So why do we want to use a binary search tree? It looks like an awful lot of trouble, much easier to use a list. Why do we want a tree? So here is one reason. I have here a list with integers. Now I want to find something in this list. Well, if it was a 123, I find it at the beginning of my list, and it just took me one comparison. I go to the front of my list and I say, is this 123? And the answer is yes, one comparison. If it was a 4, then I start at the beginning of my list and I say, is this 4? Nope, that's one comparison. Go to the next. Is this 4? Nope. Go to the next one. Is this 4? Nope. And go on until I find 4 at the end. It's a sequential search. I have to go to 1 in order to go to the next. If I count the total number of comparisons, well, to find the 123, it was 1 comparison. To find the 110, it was 2 comparisons. To find the 50, it was 3. To find the 300, it's 4. I start at the beginning. I say, is this 300? The answer is no. That's 1 comparison. Go to the next one. Is this 300? Nope, that's 2 comparisons. Go to the next one. Is 50 300? Nope, that's 3 comparisons. Go to the next one. Is this 300? Yes, that's 4 comparisons. So if I count the total number of comparisons to find absolutely everything in my list, I get this number, 1 plus 2 plus 3 plus 4, etc. And the total number is 36. Why do I want to know the total number of comparisons? Because if I divide it by the number of numbers in my list, which was 8, 2, 4, 6, I had 8 things in my list, 36 divided by 8, that gives me the average number of comparisons to find anything in the list, 4.5. So sometimes I'm lucky and I can find it with 1 comparison. Sometimes I'm very unlucky and it takes me 8, but on average it takes me 4.5. Again, I'm worrying about comparisons just as I did when I was sorting, because a comparison takes longer than any other operation, and that is going to govern the amount of time that a search will take. So if I search in a binary search tree, it's a sequential search, and I can find the number of comparisons by finding the total number of comparisons and dividing by the number of elements that I have. So how does this compare with a binary search tree? What happens now with a binary search tree? So I have the same numbers here, and I put them into a tree. So 123 goes in at the root. 110 is, I compare it with 123, it's less than 123, so I go left and I put it there. Now 50, less than 123, less than 110, it goes to the left of 110. 300, bigger than 123, goes to its right. 112, less than 123, bigger than 110, it goes to the right of 110. 245, bigger than 123, less than 300, and it goes here. 126, bigger than 123, less than 300, less than 245, put it in down there. And the 4, less than 123, so go left. Less than 110, go left. Less than 50, and it goes in here. So I have built my tree. Now I want to count the number of comparisons to find everything in this tree. So how many comparisons to find 123? So I always start at the root. Just as with a list, I always start at the head. So start at the root. Is this 123? The answer is yes. 1 comparison. How about 110? Is this 110? Nope, that's 1 comparison. And because it's less than 123, I go left. Is this 110? Yes. That's 2 comparisons. And similarly, to find the 300 takes me 2 comparisons. Is it 123? Nope. And it's bigger than 123, so I go right. Is it 300? Yes, and I found it. 2 comparisons. And if you go through this, you'll see that numbers that are on the same level take the same number of comparisons. So the root is 1, its left and right child are 2 each. Then the next level, 50, 112, and 245 are 3. And then 4 and 126 are both 4. I add this, and I find that the total number of comparisons to find everything in my list is 22. It was 36 for the list. It's 22 now, which means that the average number is 22 divided by 8. 22 divided by 8 is 3 1/8. So for our tree, the average number of comparisons is 22 divided by 8, and for the list it was 36 divided by 8. And you can see that there is quite a big difference just for 8 integers. So I can find anything in this list guaranteed 4 comparisons. 4 is the biggest number. I can find anything in this tree, with 4 comparisons. The maximum number is 4. With our list, the maximum number was 8. So I can't say anything about this list. All I can say is I can guarantee I can find anything with 8 comparisons. 8 is the number of elements there. Here I'm saying I can guarantee it with 4. So I have shorter search times with a tree. And in this information age, that is important. We are searching for information. Search times are important. I can search faster with a binary search tree, as long as it's a reasonable shape. Let's look at these 2 shapes here. This shape was from the PowerPoint. This is a binary search tree because every node has at most 2 children. Actually, in this one, everyone has 1 child. We say that this is degraded. It's degraded to a list. You have to go down this list to find anything. In fact, the best you can do is 1, 2, 3, 4, 5, 6. There's only 7 nodes in this list, but 7 is the maximum search. This is no better than a list. The one on the right here is a nice shape. This has 1, 2, 3, 4. This has 7 nodes also. So this is 7, this is 7. But with this one, this is a nice full tree. With this one, maximum number of searches to find anything in here is 1, 2, 3. All of these nodes are at level 3. So the maximum here is 3. The maximum here is 7. So this binary search tree is no better than a list. This one is very nice. We can't always get perfect, nice trees like this, but in general, a tree is better than a list. And we will see in the future that we have trees, we can tweak the trees to make them better, to make them more like this shape and less like this shape. But it depends on the order that the elements come in when you build your tree. So if you want this shape, you have to reorder your input, reorder the way that you input your data. And we'll do that later. But if your data comes, say, sorted, 1, 2, 3, 4, 5, you put that into a tree, it's going to be this shape. 1, 2 is bigger than 1, 3 is bigger than 2, 4 is bigger than 3. It's going to be this shape. And this shape, you can see it's a linked list. It's no better than a linked list. So you can't say absolutely always a tree is a better structure than a list. But usually it's better than a list, and we'll see that there are specific and very special kinds of trees that behave, that look like this shape and give us much better search times. But we're just starting to learn about trees. So why is a tree better than a list? Because you in general have shorter search times because you have fewer comparisons.